Hello, so today I'm going to talk to you about the diagnostic that I've put into LaunchPad, which is Central African Easterlies, and how these relate to Kenyan rainfall. So it's generally known that there is a dry bias in the March to May or long rainfall in CMIP, especially CMIP 5 over Kenya. So that's shown on the top. And this is the relative difference in relation to chirps rainfall. So there's this known long range dry bias in CMIP 5, and this persists into CMIP 6. And the pattern is the same. More coupled models are drier than AMIP models, and there's less of a chance of having a very wet bias than a dry bias. And also consistent between the two is the fact that April is the driest month in both seasons in models, and this is also when there should be a peak of rainfall. So using area interim reanalysis and chirps rainfall, did a study of interannual variability at the subseasonal scale. So using daily rainfall and atmospheric fields, we look at the baseline season and wet and dry composite seasons, and show that although most of the rainfall is in April, most of the change occurs in March and April. So we looked at atmospheric changes from the mean in composites to create this set of connected metrics, and this included moisture flux convergence profiles, near surface winds, mid-tropospheric winds over Central Africa, and zonal shifts in the upper tropospheric velocity potential or divergent circulation in the Indian Ocean, and a schematic of all these things and how they're related is shown on the right. But one in particular has proved to be quite interesting to look at CMIP with, and this is the Central African Easterlies. So here we have correlations between Kenyan rainfall and 700 hectopascal zonal wind over Africa. And the correlations in these three reanalyses are quite consistent in terms of the Central African Easterly correlation. And there's low correlations with winds over the Indian Ocean, especially in Mera 2 and Area Interim, which was unexpected to be at the beginning. The correlation patterns here are also similar to the correlation pattern between moist flux convergence and winds, which is quite important. And if you look at, for example, Mera 2 specifically, you can really clearly see that there are sort of two pathways here at this level. And so looking at a profile of correlations between winds and Kenyan rainfall in the south of the equator in Central Africa, the correlations are highest in the mid-troposphere, whereas to the north of the equator, there's kind of a significant chunk of correlations in the lower troposphere at a similar level to the Turkana jet, which is what Oscar is looking into. So we can think of these as two kind of pathways of either moisture transport or sort of divergent wind patterns. So at the last LaunchPad meeting, I had said I was going to look into this and showed Central African Easterly biases from Area Interim in a few CMIP 6 models. So the wetter models are at the top and the driest one is at the bottom. And it does appear that models with a more easterly wind bias, which is purple, are drier. Then looking at these across the ensemble, there is a pretty good relationship between Kenyan rainfall and Central African zonal winds at this level, in both CMIP 5 at the top and CMIP 6 on the bottom. And an important thing to note is that this relationship persists if you look at the same plot using future ensembles in both CMIP 5 and CMIP 6. So on the right we have model difference plots, so between each model's drawing a line between each model's historical coupled simulation and atmosphere-only simulation. These show that it's not just an ensemble difference between the two ensembles, but is a consistent relationship for individual models. So in CMIP 5, 87% of AMIP models are wetter and also have weaker easterlies than their counterpart in the couple ensemble, and in CMIP 6 this is 77%. So not all models will have the same sensitivities to different processes, so the consistency between model simulations is maybe more meaningful than correlations across the ensemble. But we need to set this into kind of a regional context of circulation, and the Central African Easterlies, the past study have been associated with 200 hectopascal velocity potential, which is divergent circulation. And so we've got the baseline at the top, and there's descent over North Africa, South Africa, and the Atlantic, and descent over the Western Pacific and the Warm Pool, and Northern South America. And the agreement between the three different reanalyses in these figures is very good, so I'm just showing here A5. And then in the middle we have the correlation between velocity potential and Central African Easterlies, and so weakened Central African Easterlies are positively correlated with velocity potential, so ascent over the Indian Ocean, and with negative correlations over the Atlantic. Central African Easterlies are also positively correlated with warmer Atlantic sea surface temperatures, and this figure is very similar to the correlation between Kenyan rainfall and sea surface temperatures in this month. And then looking at how sort of this background state varies, these are wet and dry composites using Kenyan rainfall for velocity potential again. So the top is the wet composite anomaly for the three reanalyses, so yellow is where they all agree in their sign. So the velocity potential anomaly in this case is kind of a dipole between the Indian and Atlantic Ocean. However, in the dry composite, it's mostly just a descent anomaly over the Western Indian Ocean, Africa, and the Atlantic. So the velocity potential anomalies are not symmetric, and this is very similar to something that I also found with the Easterlies. In reanalyses, the variation is not symmetric. So it's sort of easy to see how these changes in large-scale upper-level divergence, or ascent and descent, can be connected to Central African Easterlies. But the question is, do the models capture these patterns in the mean state, and also in terms of variability well? So here we have the mean bias and velocity potential. I'm just going to talk about the mean biases for now. For CMIP5 on the left and CMIP6 on the right. So CMIP5 atmosphere ensemble has pretty strong ensemble agreement in descent biases over the Atlantic and South America, and Northern and Southern Africa, but low agreement in the Indian Ocean. And this pattern sort of persists into CMIP6, although the descent anomalies over the Atlantic are much more localized and reduced. And then in CMIP5, the historical ensemble bias is a hemispheric pattern. However, there's not great intermodal agreement on the sign, especially in the Atlantic Ocean. However, in CMIP6, there's much more intermodal agreement in sign, and also there's a much clearer hemispheric pattern. So the historical biases in these ensembles may be connected to the biases in coupled sea surface temperatures in the Atlantic and Indian Oceans. Atlantic sea surface temperatures and their biases have been looked at quite a bit in CMIP5 and been connected to atmospheric processes and sort of biases that exist in the AMIP simulations, such as incorrect representation of stratocumulus clouds, the South Atlantic anticyclone, and anomalous surface westerlies in the Atlantic. So the off-equator dipole that you sort of have set up here between the Atlantic bias and the northwestern Indian Ocean bias might be quite important for sort of the bias and overturning between the Atlantic and Indian Oceans. And in CMIP6, there is a pretty strong relationship between the strength of this dipole and the velocity potential difference in the Atlantic. However, this is not true in CMIP5. There is considerable variability in model behavior in CMIP5, which has made it quite hard to pick out coherent relationships. And for example, two models have extremely cold biases in the Northwest Indian Ocean that make them quite different from the rest of the ensemble, and then CSIRO has a cold Atlantic bias and a descent anomaly over the Atlantic showing that although it has Central African easterlies and Kenyan rainfall that are quite similar to reanalysis and observation, that this is for the wrong reason. So while there is still an ensemble bias in sea surface temperatures in CMIP6, some models have actually much improved biases, for example, HADGEM, which has also improved its Central African easterly and rainfall biases. So here's a summary of some of the things that I've mentioned so far, but this work is ongoing and the points at the end are more about variability. So any feedback or opinions about this work would be very welcome. So both CMIP5 and CMIP6 have depressed rainfall in the long rain season in Kenya, and this is more extreme in coupled simulations and in April. Central African easterlies in the mid-troposphere are shown to vary significantly in the rainfall composites that we looked at with the area interim, and the strength of these easterlies is a good metric of how wet models will be over Kenya in CMIP 5 and 6 in the past and also in future simulations. In CMIP 5 and 6, the majority of models have stronger easterlies and lower Kenyan rainfall rates in coupled simulations, and Central African easterlies have also been associated with the upper divergent flow or velocity potential in the upper troposphere and associated mean biases. AMIP features an increased descent over the Atlantic, while coupled simulations feature ascent over the Atlantic. Sea surface temperature biases that we've related to these large-scale flow differences may be a cause for some of the coupled biases in the upper divergent flow, although this is quite complicated and needs to be understood in terms of atmosphere-only simulation biases. And then on top of the mean biases, Central African easterly strength is a feature of CMIP 5 and CMIP 6 wet and dry composites, looking at Kenyan rainfall in both the historical and future ensembles. So again, this is quite important to understand when looking at future projections. And also the upper divergent flow anomalies during Kenyan rainfall composites are symmetric in CMIP 5 coupled historical models. However, there's very low agreement in this pattern. This changes in CMIP 6, where AMIP and coupled historical composites have very similar patterns, but don't vary in the way that the reanalyses have been shown to vary. So there's still some more work to be done on this. Thanks for your time and your feedback.